Good morning, students, and welcome to my channel. My name is Mr. Meshak Ngigi, and welcome to E-Maths with Meshak Ngigi. So today we continue with our lesson that is on complex variables. And remember, in the past videos we have covered analytic functions, that is the Cauchy-Riemann's equation, and we also have the harmonic to prove that functions are harmonic. Now today we check a function from a Knec past paper that is supposed to show that a function, first of all, given one part of the function f of z, given one part, either the real or the imaginary part, and you're supposed to show if that function is harmonic. Then from there you find the conjugate, we call it the conjugate, the complex conjugate of that function fz, such that the whole function becomes analytic. All right, and we're starting that today with an example here, that given your function u x in terms of which is a function of x and y, given by exponent of negative x, then cosine of u. The first part is to show that that function is harmonic. Then the second part is to determine the conjugate, that is the v into a function of x and y, such that the function f of z given by that is analytic. All right, now so solution. So you know, for a function to be harmonic, so this function is given, it is a real function. So therefore, we know for it to be harmonic, then it has to satisfy this equation. So plus squared v, then that is u, sorry, because it is a function of u. It should be 0. Okay, so therefore we have this function differentiated twice, then differentiated twice with respect to y. So du dx. So again, remember, we only deal with the x, the function that has an x part. So we only differentiate the exponent, treating cosine of y as a constant. Okay, so we have our value here is -1. So drop -1, which is just negative. You don't have to write the 1. Then exponent of negative x, then cosine of y. All right. Then again, du dx now squared, that is differentiate the second time. Again, drop a negative. So if you drop a negative, this part becomes positive, so you remain with e negative x cosine of y. So you can see we have not tampered with the cosine function. Right, together. Now again, with respect to du with respect to y. So in this case, again, we only differentiate the cosine of y. Are we together? We don't interfere with the exponent. So when you differentiate cos, you get a negative of sine. Are we together? So the negative comes there, then e negative x, this one becomes sine of y. Then you come to the second part. So second derivative with respect to y. Now again, differentiate the sine of y. Right? When you differentiate sine, you get a positive of cos. So the negative here remains. So we have e negative x cosine of y. Then from that point, add. So we take our du dx squared, du dy, then the second derivatives, then add the two of them. The answer should give you 0 for that function to be harmonic. So our du dx squared is given by this. So e negative x cosine of y. Then you have plus negative of e negative x cosine of y. So therefore, what does this give you? So we know this term and this term, first of all, are the same. Then you have a positive, you have a negative. So when you open this bracket, you get a what? You get a negative. So you'll have e negative x cosine of y minus e negative x cosine of y. And since these two are the same, therefore your answer gives you what? Your answer gives you 0. Right, together. So that is the first part of the question. Now let's get to the second part. So the second part is you're supposed to show you're supposed to find the function v, that is the imaginary part of the function, so that the whole of this function, taking your u and taking your v, the function becomes analytic. Right, together. So now for you to find that, so now we have a properties. We have two properties that are supposed to be fulfilled for a function to be analytic. We know that du, remember these are partial derivatives. Are we together? So du dx should be the same as dv dy. That is first of all. Then the second one is dv dx should be the same as negative of du dy. y. So those two conditions have to be met for a function to be analytic. Now this is very important because this is where you start solving for v. Why? Because we know we start with the first condition to be met. du dx should be the same as dv dy. Right, together. Du dx should be the same as dv dy. So if our du dx is the same as dv dy, so what is our dv dy? So we come to du dx. What did we find as our du dx? Negative exponent of x cosine of y. So therefore, if your du, so if your du dx is the same, so therefore we are saying that also your dv dy should be the same as negative of negative x cosine of y, because these and these are the same. Now this function is already a derivative, right, together. So for us to go back to the original function of v, okay, for us to go to the original function of v, then we are saying we should integrate this function for us to go back to v. So for us to get our v, okay, now integrate cosine of y, but now what is in terms of the derivative is dy. Are you together? Yes. So therefore your v will be given by, so integrating cos, when you integrate cos you get sine. Are you together? Integrating cos gives you a sine. So you just have negative e negative x sine of what? Sine of y. Write it with a constant, and our constant here will be written as x. Anytime you integrate a function, you must have, as long as you don't have the limits, you must have a constant of integration. Okay, so our constant here will be given by that. Now our v, remember our v here is in terms of x, and our v is in terms of x and y. That is why we just introduce, we have an x here, we have a y here by the end of the day. So again, we introduced a constant with respect to x because we have differentiated with respect to y. We've integrated with respect to y. Now, if this is our v, all right, if this is our v, then we already have a dv dy. What don't we have? We don't have a dv dx. Now let's find dv dx so that we can compare it with our du dy. Remember, we are comparing these two. We have already compared this, which has led us to this. Then we compared these two derivatives, then we see what it will give us. So dv with respect now to x, differentiate the function again with respect to x now. So remember, when you differentiate, you drop the power. So you have e negative x, because when you drop a negative, it gives you a positive. So then sine of y gives you, now remember this, differentiate this. Now it is a constant, yes, but we cannot assume it is a constant without a variable of x, because we are integrated with respect to y. So we'll say also this one is just a derivative. Okay, so we have the constant here, but we have the derivative. So we have differentiated this part, then also differentiate this part, because we have, so we shall have a prime x to show that this one has been differentiated. Now from that point we can now compare our two functions, because we know that dv dx should be the same as negative of du dy. So now let's come to dv dx. It is this. So we have e negative x sine of y plus the derivative of a function equals to, now negative, our du dy is this. So negative e negative x sine of y. Are we together? So therefore e negative x sine of y plus a constant derivative. So we have e negative of x sine of y. Remember, the negative gives you what? Gives you positive. Now why do we have to compare these two functions? This is because we have to find a function, because at some times you might find there is a constant with respect to the variable of x, which was supposed to be at the end of this function here. So when we compare The comparison of the second comparison is to enable us to get the constant. What was our constant term? But remember, it is not necessarily a constant. It can be a variable with respect to x, because here we are differentiated with respect to y. So we now compare the two terms. We have e negative sine y, e negative x, then we have sine y, then e negative x. So the first part and the second part are the same. That is true. So what is our a prime of x? So do we have any function added here? No. So our function is 0. Therefore, our a, so suppose here, since we have a derivative, if we had a function here, we could integrate here so that we remain with the constant. But since our function is 0 on the other side, therefore, if we even integrate the function ax, you still get a what? You still get a 0. Therefore, your v xy will be given by, remember our function we were supposed to find, so I was saying this second comparison was supposed to help us to get this variable here, or the constant. So therefore we know that our vx, so it will be given by negative e negative x, right, sine of y, but we don't have a what? We don't have a constant, so plus 0. Therefore this whole function, for it to be analytic, therefore your function fz will be given by, what was our u? Our u was this, so we have e negative x cosine of y. Then what is our v? Negative e negative x sine of y, right? Therefore, then remember we have a what? We have a j. So therefore your function f of z is given by that. Students, that is how you find if a function is harmonic, and also find the other conjugate so that the function that you get proves to be analytic. Let's check a second example. Now we check a second example on complex variables, on harmonic and analytic functions. Now our example 2, which we have here, we checked on example 1, kindly check on that. Example 2 says we have a function u, which is a real part of a complex function. So you show that that function is harmonic, then you find the complex conjugate in the function, right, such the whole function is analytic. So solution, again, so we know for a function to be harmonic, these are real functions, so we know this should give us d squared u dx squared plus d squared u over dy squared. The answer should be what? Should be 0. So we have our function, then let's differentiate it twice with respect to x and also with respect to y. So we have du dx. Remember, this is partial derivatives. So with respect to x, we shall have 3x squared, y, then we have minus what? Minus y cubed. Right, together. Then second time, u dx squared. So we shall have, again, this will give us 6x, y. There is no x here. So it is the same as saying you are differentiating a constant, so it gives you 0. So you only differentiate the first part. Then you have du with respect to y. Now differentiate the function here with respect to y. So you have the first part, which will give us x cubed, all right, because you only have y with the power of 1. So you drop the power, reduce the power by 1, you have y to power 0, and anything to power 0 is always 1. Okay, then minus 3y squared x. All right, so remember the rule of differentiation: drop the power, reduce the power by 1, but this is partial derivatives. So again, d squared u dy squared will give us, you don't have a y here, so you don't differentiate this part, so you only differentiate the part here. So remember, a number carries a sign before it, right, together. So the negative appears here, so you have a negative. This part is 0, okay, so you don't integrate it, but you have to integrate this part. So you have negative 6xy. So I've just rearranged, I've just brought here, but remember, you drop the power, it gives you 6, then this one comes to power 1. So therefore, we know this plus this gives you 0. So 6xy plus negative 6xy. That one should give you what? Should give you 0. So you open the bracket, you have 6xy minus 6xy, and definitely your answer is what? Your answer is 0. Then you go to the second part, so that is 1, so proven. So hence harmonic. Okay, hence harmonic. All right, then you go to the second part. Again, remember, for a function to be analytic, two conditions have to be met. du dx should be the same as dv dy, and not du but dv dx should be the same as negative of du dy. These are partial derivatives. Again, always keep that in mind. Now we can find our function. No, so we are saying again, we shall use the first property, then the second. The first property is just to help us to kickstart in finding vxy. So we know our du dx should be the same as dv dy. Therefore, what is your dv dy? So you just come to du dx because they are the same. So du dx. So du dx is given by 3x squared y minus y what? Minus y cubed. All right. These and these are the same, so therefore you have this. Now, for us to go back to v, these are the derivative, okay? So let us go back to v. So our v in terms of xy will be given by, so integrate this function, is given by the integral of 3x squared y minus y cubed dy. Remember, you're integrating with respect to the value here, the variable, because this one is dv dy. So you integrate with respect to y. And what is the rule of integration? The rule of integration is, so remember, this is different from, so in this part, let me just go directly so that I don't confuse you. You increase the power, then you divide by the new power. Right? Increase the power, divide by the new power. Remember, we're integrating with respect to what? With respect to y. So therefore, your v xy will be given by increase the power of 1 of y, then divide by the new power. So it is to power 1 now. So it becomes to power 2. So you'll have 3x squared y squared, then divide by the new power. So you can just have our 2 there. Then minus, this one is power 3, increase it, becomes to power 4, then divide by new power. Then plus constant, now we'll put it with respect to x. Remember, this is supposed to be a function of x and what? X and y. And you can see we have x variables. So we'll put it in terms of x because we shall use the second relationship for us to get the variable. So we'll not have a change in the values of what? In the values of y. Are we together? The values of y will not change. This part of the function will not change. So what we'll just need to find will be the constant here. This one is the constant of integration, sorry. There's no prime. So our v is given by that. So if you just rewrite it so that you can have your, so this one is 3 over 2 x squared y squared minus 1 over 4 y to power 4 plus ax. That is a constant of integration. Now, let's go now. So we have vxy. Now, our vxy should have a variable here. So for us to get this constant here, then we compare these two. So we now get dv dx, all right? Because we already have v. Now let's get dv dx, dv dx. So again, differentiate this function, differentiate with respect to x, and we say drop the power, reduce the power by 1. So you have 2, so you drop 2, you remain with 3 here. Then x, y squared. Right, together. You drop a 2, the 2 and the 2 cancels, you remain with 3. Then x reduces power by 1, then y is a constant, it remains. This function here has only what? It has only y, so you don't differentiate it because there is no x variable here. Then prime, so plus a prime x, because the differential of this is given by a prime x. Then compare dv dx with negative of du dy. So dv dx, so we're saying compare this with this, right, together. So just compare the two. So dv dx is given by this, so it is 3xy squared plus a prime of x should be the same as negative of du dy. Negative of du dy, negative of du dy is this, okay? So it's x cubed minus 3y squared x. All right? Yes. dv dx negative du dy. So So open the bracket. So 3x squared y squared plus a prime x, okay, equals to negative x cubed plus, because negative gives you positive, so 3y squared x. Now compare the two. You can rearrange it maybe also. I've just rearranged the positive was started and the negative followed. So you can see this part and this part are the same. So therefore your a prime of x will be given by what? Negative of x cubed. You see now? So a prime x will be given by negative of x cubed. Now, how do you get ax? Remember, we're supposed to get ax. This one is a prime. Integrate both sides. So ax here will be given by, remember you're integrating with respect to x. So when you integrate, increase the power by 1, divide by the new power. So it is negative x to the power 4, then over 4. Right? In this case, we don't put another constant of integration. Right, together? Yeah, you don't add another constant and you're finding a constant. So so this will be given by this. So your ax will be given by negative of 1 over 4 x to the power 4. Therefore, now you can rewrite the whole function f of z. So f of z in that case, let me start with vxy. So your vxy will be given by, so what was your v? This function. So 3 over 2 x squared y squared, then minus 1 over 4 1 over 4 y to the power 4, then plus, remember we now have our constant here, and our constant will be given by negative, so we'll have a negative now here, negative 1 over 4 x to the power 4. Therefore your whole function f of z will be given by, you have your x, so it is x, your y, your u, sorry, y minus y cubed x. Then that is the real part, okay? Then we have plus, we can bracket this, 3 over 2 x squared y squared minus 1 over 4 y to the power 4, then minus 1 over 4 x to the power 4 into bracket j. So your function f of z, the real part and the imaginary part, when you put the two of them together, then we say that is the complete function of f of z. And students, that is how we work out any function to prove it that is harmonic. Then the second part, find the other complex conjugate for that function, that particular function to be, analytic. And that marks the end of harmonic and analytic. Now in the next lesson, so that you can keep touch, you're going now to be checking transformation, that is the inverse transformation and also bilinear transformation. So thank you. If you have not subscribed to the channel, kindly subscribe, share and also comment. Thank you. See you in the next lesson.